So this next section talks about limits involving infinity and asymptotes of graphs. And so back in college algebra, you looked at graphing rational functions. And rational functions we saw could have vertical asymptotes, it could have horizontal asymptotes. We even looked at having sometimes slant asymptotes. So there's a couple things that we want to do. So let me pull up an example and let's just look at one first by just looking at a graph and answering the following questions. Okay, so in front of us is a graph, and the graph is y equals, our numerator is x cubed plus 1, our denominator is x plus 3, all times x minus 1 quantity squared. And so we can see that there's these vertical asymptotes. Vertical asymptotes occur, recall, let's say at some x equals a, if, so let's put this in terms that we've been using, limits. The limit as x approaches a, let's say from the left-hand side of f of x, goes to either positive or negative infinity. Same thing with the limit as x is approaching that value of a where the vertical asymptote exists on the right-hand side. And so notice in this picture we have two vertical asymptotes. And those were denoted by that dotted line. So those really aren't on the graph. It's just denoting that that graph is getting really, really close to that x value, but never touching or crossing. And so we can say that here, if I'm looking at the limit as x is approaching -3 on the left-hand side of this function f of x, notice that as I'm getting closer and closer to -3 on the left, that this graph is shooting downwards. It's getting smaller and smaller and smaller. This is going off to negative infinity. So recall, the limit didn't exist if it wasn't going to one particular number. But because we like to know what's going on with a graph, if it's going to infinity or negative infinity, even though it doesn't exist, we like to state where it's going. If we look though at the limit as x is approaching 3 from the right-hand side, so coming in, sorry, -3, 1 and -3, coming into -3 on the right-hand side, notice that if we follow the graph on the right-hand side, this is shooting upwards. It's going off to positive infinity. We can see we have another vertical asymptote, right, at 1. And the limit as x approaches 1 on the left, this one shoots up to positive infinity. Same thing if we're coming in on the right-hand side. This is also shooting off to positive infinity. So this graph also has what is called a horizontal asymptote. So horizontal asymptotes, and I'm just going to denote it HA. These occur if we look at the limit as x approaches positive infinity of our function. And this gives us, it gets closer and closer to one y value, let's say c. C, a real number. Same sort of idea as we're going to pause our negative infinity limit as x approaches negative infinity of f of x. This would also go to one y value of c. And it actually might not be, yeah, it will be. I'm just trying to think, will it always be the same thing and it not necessarily? So I'll just say D. Okay. If we look at our graph that we were given, and we look at the limit as x is going to positive infinity, we want to see, does it look like it's getting closer and closer to one y value? And it does. As we're going to positive infinity, notice that this graph is getting closer and closer to my x-axis. So it's getting closer and closer to y equals 0. So the limit as x goes to positive infinity of our graph of f of x, this is equal to 0. And the limit as x is approaching negative infinity of f of x. So same idea, if we follow the graph as x is going off to negative infinity, notice that this is getting closer and closer to our x-axis. So this is also equal to 0. Okay. Let's say we wanted to look at the limit as x approaches 0. X squared plus 1 all over x plus 3 all times x minus 1 squared. I can see on my graph that it's continuous there. There's no jump, there's no open circle. I can't really tell. I know that that y value is between 0 and 1, but I can't really tell what it is. So let's just go through and let's just do our direct substitution. So doing our direct substitution, we're good if it comes out with a number. The only thing, if it's an indeterminate form, then we got to worry about it. But let's see. I don't think we get an indeterminate form. So if we plug in 0 wherever we see an x, we get 0 squared plus 1 in the numerator, all over 0 plus 3 in parentheses, all times 0 minus 1 quantity squared. So simplifying, I see I have 1 in my numerator. And we have 3 all times negative 1 squared. Well, that's positive 1. And positive 1 times 3 is 3. So we have 1/3. So that kind of was a review on vertical and horizontal asymptotes of what's going on as you're looking at a picture and describing them in mathematical language using limits. Now that we have calculus, we can do that. So let's review how we find asymptotes. For vertical asymptotes, how we can find horizontal asymptotes. And then I'm going to give you some tricks, if we have time, on how to find horizontal asymptotes. Okay, so recall vertical asymptotes. So vertical asymptotes of a rational function may be found by examining the factors of the denominator that are not common to factors of the numerator. Vertical asymptotes occur at zeros of such factors. Okay, so recall if we had factors, we're working with a rational function and we had plugged in some value of c, we got 0 over 0. We saw that if we factored that we had common factors and we could cancel it. So as long as we don't have common factors, the values that set our denominator equals 0, but not also a numerator, are going to be vertical asymptotes. Okay, so how to, given a rational function, identify any vertical asymptotes of the graph. So we're going to do this by, first thing, you want to factor both your numerator and denominator, if possible. Note any restrictions in the domain of the function. So we have to exclude certain values of x, and those are values which set our denominator 0. Then we can reduce our expression by canceling common factors in the numerator and denominator. So note any values that cause the denominator to be 0 in the simplified version. These are the vertical asymptotes. Note any restrictions in the domain where asymptotes do not occur. These are removable discontinuities. Basically, when we were looking at this, so let's say we have the following. Let's just start actually easy. Y equals 1 over, I don't remember what I was going to say, 1 over x. So notice that there's nothing that sets my numerator equals 0 and my denominator is equal 0 when x is 0. So our domain, x can't be 0. Okay, so all numbers except for x equals 0. So we want to see what type of asymptote this is. We actually have a vertical asymptote at x equals 0. So let's look at what's happening as a limit as x is approaching 0 on the left-hand side. Think about this for a second. What type of numbers you're plugging in. Notice that we're plugging in numbers that are less than 0, so they're negative. And so if I put 1 over a negative number, I notice that I'm getting back a negative number. So if you put in numbers that are getting close to 0, think about this also. If we have 1 over 1/2, this is the same thing as 2. If I even choose something closer to 0, so let's say 1/3, 1/3 is closer to 0 than 1/2. So then I get back 3. But if these were negative, then my numbers are negative. So even getting closer, if I did 1/4 or negative 1/4, when I divide 1 divided by that, it's going to be -4. So these are going to be blowing, they're shooting down to negative infinity. If we look at the limit as x is going to 0 on the right-hand side, of 1 over x, well, we're plugging in values which are greater than 0. They're positive, getting close to 0. So those are going to be blowing up to positive infinity. So we know as we're getting closer and closer to 0, we're going down. And we know as we're getting closer and closer to 0 here, we're shooting upwards. Let's look at the limit as x goes to positive infinity. See, this is where you just got to keep imagining what's going on. So if we start plugging in numbers as x is going to positive infinity. So like if I plugged in 100, that's just easy for 1 over x. So this, if I plug in 100, that's 1 over 100.
I think the screen share might be frozen.
Yeah, I think you're right.
And it's pretty much the time to stop anyways. That's not good. This is the 3rd day in a row Um,
After class, I have some things that might be able to help with that. So if you
Okay.
want to stick around and talk about it.
Okay. I think it's. I'm just gonna pause.